issue after a few epochs. And some people say about the out of memory after the second epoch. Some say out of the 10th epoch. Is probably somewhere in the code could probably contain some memory leak. I'll double check the code and see if we need to modify anything in the starter code. Question?
Can we get an extension if there's a problem with the start code?
I actually don't think it's necessary because if you use the frozen setting, some students are already able to get 90% accuracy, and that part is okay. So I think it's not necessary to use the flexible option. So you can just use the frozen option and then report the performance. And, yeah. Actually, there are still more than 2 weeks until the deadline, so there are still plenty of time. So, and also for the question 2 in the in the assignment 3, which was the ASR, we highly recommend using SpeechBrain. And SpeechBrain is very easy to use. It's just it's similar to automodel for causal language model, but it's loading a transformer model that is pre-trained for automatic speech recognition, and it's actually able to be finished within just 10 lines of code. So the heavy part is the discussion. So analyzing which part this model is able to, which type of input this model is able to handle, and which is, in which scenario it fails to recognize the speech. So whether it is code switching, or whether it is some slurred speech, whether it's some fillers or within the sentences, the discussions of this type is very important. So in the last lecture, we looked at some problem setting of speech recognition. So speech recognition is the problem that converts speech into text, and we described some speech features and describes a noisy channel for automatic speech recognition. So we actually described 2 models. So the first model was a maximum similarity search model, where in the maximum similarity search model, we assume that every single word contains only one possible sound. So we can just look it up in the dictionary when we hear a sound and find the corresponding word in the dictionary that has the maximum similarity between the input sound. But this assumption does not really hold because one word could contain a lot of different ways to be verbalized. So in that case, we use an acoustic model, which models P of X given W. So with the help of this acoustic model, we will be able to build a noisy channel model for speech recognition. So this noisy channel model uses the Bayes rule to flip the position of X and W in the probability. So with the help of the acoustic model, P of X given W, and a language model, P of W, we'll be able to handle the speech recognition, which is to find the maximally similar word given the sound. So P of it is a maximum probability search based on the posterior probability. So there are some limitations of these models. So first, we still need a lot of data to model the probabilities of X given W, which is the acoustic model. And also the maximum search step takes a lot of time. And this problem is aggravated by some non-standard spelling. So you will need to have a lot more items in the dictionary or the vocabulary, which further increases the data requirements. Recently, Richard Sutton, which is a brilliant professor at Alberta University, summarized a bitter lesson in the developments of machine learning. So he says that it is better to just rely on deep neural networks to learn by itself. So previously, people tried to engineer all sorts of different features. And the features represent how the scientists and the engineers understand the nature of the data and the nature of this problem, and also how to go about to solve these type of problems. But it seems like the carving of these types of features are extremely expensive. We'll get to your question in 1 minute. These types of these type of features are extremely expensive compared to the abundant data that is available to be passed into the deep neural networks. So the deep neural networks are able to automatically capture the patterns that occur in the massive data, and deep neural networks are able to process the data sets that are actually several magnitudes larger than all the data that each human being is able to see throughout the course of his life. So it is kind of understandable that the deep neural networks usually lead to much better performances. So the bitter lesson is that it's better to just rely on deep neural networks, learn by itself. So question?
Yeah, so where, I don't really remember, where does the next step, where does that step appears in last lecture's model?
Last lecture's model was the noisy channel speech recognition model. So
where did we use that step? What did we use it for?
We use so this is the acoustic model, and the noisy channel model was essentially this one. So search for the maximally similar word based on the maximizing the posterior probability, which equals the prior times the likelihood divided by the evidence, and the evidence is constant. So because there's no W here, so we really need to only maximize the denominator, which are the product of these two probabilities. And actually, the P of W can be computed by a language model. And actually, the language model also requires a lot of data to compute. And also P of X given W, this acoustic model also involves a lot of data. So essentially,
it involves looking through all possible W's.
yes, looking through all sort of words in the vocabulary. So it's better to just rely on deep neural network to learn by itself. And this is the principle behind this end-to-end model called LAS, listen, attend, spell. So in the next 10 minutes, we're going to go through this listen, attend, spell model. So this is an end-to-end model. Actually, the term end-to-end is actually highly overloaded. And many people use end-to-end to describe end-to-end as a marketing term. And here I'm describing end-to-end as development of this model where you only train once. You only build one model and then train once. So the input to this model could be either the features or the sound waves. And the output of this end-to-end model is specified as text in order to do the end-to-end automatic speech recognition model. Because the definition of speech recognition model is text is the sound or features in and text out. So when you build an end-to-end model, you directly build a model that takes in sound or features and output text. So there is no assembling of components. So what I mean by no assembling is that you have these types of components and put them together into the model and train them, all of them at once directly. So there's no need to first train some components on some pre-training task and then assemble them together to do some transfer learning. It's not necessary to do this type of assembling. So actually, some people use end-to-end as a marketing term. So they use the transfer learning as a building component, and then they still claim that their models are end-to-end. So this is not really the correct definition of end-to-end. So end-to-end is just you build one model, and this model is trained once, and this model is able to directly get the output that you want from your input. So sequence-to-sequence model are typically end-to-end. So the listen-attend spell model follows this schematic architecture. So on the neural network model side, there is an encoder and a decoder. So the encoder and decoders are deep neural networks. The encoder is, so both of them are recurrent neural networks. I will describe the details of the recurrent neural networks in the next slide. So the encoder's input are some sequences of features. So these features are computed by the feature computation part. And this feature computation part uses some traditional features that are used in speech recognition, which are log-mail spectrum. And there are 80 this kind of features in total. So why do they use these types of features? So first, this type of MFCC features occur on the frequency domain. And the patterns in speech or other sound-based data are very easy to be captured in the frequency domain or the spectrum, because sounds are essentially oscillations, and oscillations can be decomposed into superpositions of sinusoidal oscillations. And each sinusoidal oscillation in time domain actually corresponds to one single pulse in the frequency domain. So if you analyze this kind of oscillations in frequency domain, then the data is going to be much more regular than they occur on the time domain, which is actually desired. So usually the first thing that they do is to convert everything into the frequency domain using Fourier transform. And after that, they use the MFCC features to simulate how much energy is carried through the oscillations of the sound at every single frequency band. So these 80 MFCC features describe how much your eardrum is vibrated by the sound oscillations at some particular frequencies. So by computing these kind of features, we are simulating how human ears are hearing the sound. And these types of features are very useful for humans recognizing the speech. And therefore, and the intuition is that it is also going to be useful for machines to recognize the speech. But these types of features are still come up together to be very long sequences. So they do some subsampling and result in some shorter sequences. And then they pass in the shorter sequences of the text or of the features into the encoder. So are there any questions about the encoder and the features that are passed into the encoder? Yeah, question?
So the feature computation is using the NFC feature from the spectrum?
Yes. The NFC features can be computed in an off-the-shelf manner through, for example, SpeechBrain, and some. There are also some convenient packages like Librosa, and the details for computing MFCC is not in the exam. Yeah. Welcome. Okay, let's take a look at the decoder. So here the decoder does the autoregressive generation. By autoregressive, I mean there are a lot of steps in the generation. In each step, you have some input, and it predicts the next step output. It's just similar to the causal language modeling. But instead of predicting the next token, here the decoder predicts the next character. So this is the character-based decoding, autoregressive decoding decoder. And after the next token is predicted, it concatenates the next token to the input and repeats this process, so it is able to predict even the next token. So this is this kind of iteration process is called autoregression. So in this autoregressive manner, this decoder is able to decode the whole sequence based on some correct representations of the encoder. So at every step, this decoder essentially computes the probability of the next token given the tokens up to now and the input. So the inputs are actually represented by the representations of the encoder, and the encoder takes in the features, and the features are computed by this kind of complex feature computation part. So in the last lecture, there was a question about the feature computation. So the feature computation, MFCC is not the only possible feature that you can compute. And some people use the convolutional neural networks to automatically compute the features. And the CNN also sort of converts the oscillation in time domain into some sort of spectrum representations. And when the parameters of the convolutional neural networks are optimized properly, it is able to achieve similar effect as the spectrum feature computation. So another question is why do we use the character-based decoding instead of the token-based decoding? And one of the reasons for using character-based decoding is that this saves the computation memory. So if you use the character-based decoding, then we don't really need a very large linear head at the end of the decoder. Whereas if you use a word-based decoding scheme, then you need a massive projection layer. For example, 768 times 32,000 dimensions. This kind of massive classification head is actually consumes most of the memory, and a large portion of the model's parameters in the transformers are this kind of the language model head. So back to the decisions of using character-based decoding instead of the word-based decoding, the benefit is the saved memory and computation. So this architecture was proposed several years ago, and I think it was 2016, 2017. So at that time, we didn't really have the large computation infrastructure that are comparable to today. So today, every single personal computer, so it's kind of easy to get a computation, a graphic card with 8 gigabytes of memory or even 16 gigabytes. And those GPUs that are in the data warehouse can have up to 60 gigabytes or even larger. But at that time, it's very luxury to even have 4 gigabytes of memory in the GPU. So it's very necessary to have some smaller models. And the character-based decoding actually contributes to reducing the size of the models. So let's take a look at the details of setting up the encoder and decoders. So the encoder, which the authors refer to as the listener, is a pyramidal bidirectional long short-term memory. So long short-term memory is a recurrent neural network, essentially with attentions. And this is connected bidirectionally because the authors want this model to capture both the forward and backward dependencies between the time steps. And also this encoder is pyramidal. So as you can see from the picture on the right-hand side, when we go up by one layer, the steps is 2 steps are combined into 1 step. So effectively, the sequence length is reduced by half. So after you go up with, let's say, 5 layers, then you only have 1/32 of the sequence length. This makes it a lot easier for the deep neural networks to capture what happens out there in the long sequences. And eventually, the output of the listeners are pulled into a fixed length vector. And this fixed length vector is passed into the decoder as part of the input. So the decoder is a recurrent neural network with attentions. So you might want to ask, why does the decoder use RNN with attentions, not an LSTM? And the encoder, why does the encoder use RNN with attentions, but a bidirectional LSTM? So part of the reason is that the authors tried a lot of different combinations of models, and they found that this combination of model works the best. And actually, this kind of design choices in building the models differs from problems to problems. And in some problems, perhaps an RNN with attention encoder and a pyramidal bidirectional LSTM decoder might work better. But it really depends on the actual problems that you are trying to solve. So we really need to try different models and validate them on the validation set and figure out the best model to use and then implement that and ship this product. So the learning is through teacher forcing. So the teacher forcing step is the same as what you did in assignment 2. So at every step, this model predicts the next character, and we train these parameters of the model to maximize the log probability of the correct next token, given the correct previous the next correct next character, given the correct previous characters. Of course, the input sequence or the sounds and its features thereof are part of the conditions as well. So this is the teacher forcing learning scheme. So in this teacher forcing, we assume that the input character sequences, the generated character sequences are correct, whereas there are some other types of learning scheme that allows the generated characters that are passed as part of the input to the decoders to be wrong. But in this teacher forcing, we only consider the inputs to be the correct character sequences. So the model performances were on the noisy Google Voice search task was pretty good, but at that time of this paper, there was still not as good as COD and hidden mark. Performance of speech recognition model were measured by the word error rate, and this is actually different from the evaluation of machine translation systems. So word error rates are some numbers that counts how much error that you make. So a lower word error rate is better. But for machine translation, there are usually a lot of different references. So the blue score is more suitable for that scenarios. And also the speech recognition and the machine translations were very different research directions in the past few years. So although very recently both of them can be solved by very deep neural networks, but 10 years ago, 20 years ago, they were very different fields, and they were very different groups of people working on the corresponding directions. So in every single group, people were just following the precedence of setting up the evaluation leaderboard and using the evaluations scores. So as an analogy, the people working in classification uses probably accuracy, and some people use the precision and recall, whereas in the information retrieval, we will talk about information retrieval in next week. In information retrieval, people care about a sort of different evaluation metrics. So the point is that in different problem settings, different groups of people are working on them. So it's natural that they agree to use different evaluation metrics. And word error rate is considered the traditional performance metric to evaluate the automatic speech recognition systems. But there are some debates though. So in the future, I won't be surprised if some group of people says that we should use GPT-4 or 5 to evaluate the performance of any deep neural network-based system. And I won't be surprised if something like that come out in the next few years. But until then, let's still use word error rate to evaluate the performance of automatic speech recognition systems. 3 years after the LAS model was proposed, some other group of people used some new data and new engineering to make LAS achieve state-of-the-art in automatic speech recognition. So here you can see that the word error rate is reduced to around 5.6 compared to the 8 of the hidden Markov model's performance. So now they really achieve the state-of-the-art. And actually, until now, listen, attend, spell is still the state-of-the-art in automatic speech, in many of the automatic speech recognition benchmarks. The OpenAI's model Whisper, which is based on transformers, claim to achieve SOTA in some tasks, but not on many other tasks. So up to now, the LLS, which based on long short-term memory or recurrent neural networks, are still a very robust and a strong state-of-the-art. So there are some recent topics in ASR. The ASR systems need to be robust towards different types of noise. For example, there are some differences in the recording device. And this kind of difference might not appear very salient to humans. For example, when I talk with this microphone or with the microphone on the podium, you can still understand what I'm saying. But it's very hard for the automatic speech recognition systems to understand what we are saying if we switch the microphone, because that actually changes a lot of the encodings and the patterns inside the speech data, and that is causing some sort of shifting in the distribution of the data, which usually result in a strong decrease in the ASR performance. And there's also the multiple speakers problem. So you first need to do the speaker diarization, which separates the audios of different speakers, and then do the ASRs respectively. So you can try to do the ASRs with the speakers where multiple people are talking together, but the transcripts are going to look very messy. And there is the code switching problem. So code switching involves mixing some languages. So this effect is especially popular with bilingual speakers or multilingual speakers. So not all of those languages are mastered at the same level of fluency, and sometimes some words can occur easier to be retrieved from your memory than this word from another language. So when you are speaking another language, and you want to mention that word, you might just come up with this word occurring in this language. So this results in code switching within the sentences. And this is actually very hard to recognize for the ASR systems, because when code switching happens, this ASR model intrinsically needs to handle the multilingual case. It actually needs to do the ASRs in either of these two languages. Actually, some of the modern ASR systems are able to handle that. So if you try to transcribe some sentences in like WhatsApp or Messenger or WeChat, then some of them actually are able to handle the code switching between English and other languages. But for assignment 3's the second question, please don't use this kind of social media apps because there's no coding components involved. We highly recommend using SpeechBrain. Actually, the coding component in SpeechBrain is not that much. It's able to be done in less than 10 lines, but it gives you 3 more marks if you use SpeechBrain. So, and there is a voice privacy challenge which tries to protect the user's identity without sacrificing the ASR performance. So our voice contains a lot of patterns about humans. So it's kind of possible to recognize who we are from how we speak. So we need to add some noise to essentially prevent ourselves from being recognized by the detectors. But this process should be done without sacrification of the ASR performance. So let's take a look at how to evaluate the system performance. If somebody says how to recognize speech, but an ASR system outputs how to rec a nice speech, then only 2 out of the 4 words were correctly transcribed. Can we directly quantify that using the accuracy, like 2 out of 4 or 50%? Not necessarily true, because even if you have a system that captures 100% of the accuracy, this AR system might still produce a lot of garbage. So the accuracy in this case encourages hallucination. So using accuracy does not capture the whole picture of the speech recognition. And when measuring the performance, we need to measure different types of errors that this system is able to commit. For example, insertion, deletion, or substitution. So the insertion is the hallucination, and deletion is the failure to include some words that are spoken in the transcript. So if you skip some input, you essentially commit a deletion error. And there is also the substitution error, which is the traditional sense of incorrect transcription. When you hear a word and you mistook that for another, that is the substitution error. So these types of errors sometimes are interestingly related, because you might see that the substitution errors is essentially a deletion followed by an insertion. So, or you can say it's a insertion followed by a deletion. So when computing the word error rate, we consider the minimum possible combinations of the number of substitution and number of insertion and number of deletion, and divided them by the number of words in the reference and multiplied by 100. So usually people use people weight the substitution error to, for example, 5 times as much as an insertion or deletion error, so that the evaluator will not be biased to count some insertion error or deletion errors into some substitution errors. But for the purpose of the next few slides, we are just going to say an substitution error has the equal weight as the insertion error or the deletion error. So to compute the word error rate, we need to sum up the 3 types of errors to get a number n, and divide that by the number of reference, the number of words in the reference, and multiply by 100. So this sum of the 3 types of errors is called added distance, or the Levenstein distance. And this is the minimum possible number of the 3 types of errors to edit the hypothesis into the reference. Or you can equivalently say this is the minimum number of samples to edit the reference into the hypothesis. But if you flip the reference and the hypothesis, then the number of insertion errors and the number of deletions errors are flipped as well. And interestingly, if you use some packages that compute the Levenshtein distance for you, you should be very careful when specifying which is the hypothesis and which is the reference. But the total number, but the added distance is the same. And the number of substitutions is the same. It's just that if you flip the hypothesis and the reference, then the number of insertion errors and the number of deletion errors are going to be flipped as well. So the computation of the added distance can be done by a dynamic programming. Dynamic programming algorithm contains a base case where you easily know the answer, and an induction step which converts a big problem into a smaller problem. So when you apply this induction step iteratively, you can eventually reduce the large, difficult dynamic programming problem into the base case, which is a very, very small problem where you can easily know the answer. And there are some assumptions that hold true before and after this induction step. So which is the big problem and the smaller problems are still the same problems. So in the algorithm to compute the word error rate or the added distance, we can state the big problem as computing large n of the n of n and n. So the small n indexes the reference R, and the small m indexes the hypothesis H. So I'm color coding the reference as into blue and the hypothesis into green to make it easier to tell apart between n and m. So a smaller problem is to compute n of n-1 and m-1. This is the added distance between the reference all the way until the last word. So all reference excluding the last word, and all the hypothesis excluding the last word. So this is still the added distance, but this problem is slightly smaller than the bigger problem. So if we continue this induction step, we will eventually go towards a base case where we either compute n of 0 m, or we compute n of n0. So in either case, we will know the answer easily, as we will describe in the initialization. So if you know the answers to a smaller problem, then you can use an induction step to solve the bigger problem. And this induction step involves an if-else statement. So this if-else statement considers the last word in the reference and the last word in the hypothesis. If these two last words equal each other, then the added distance of the larger problem is actually equals the added distance of the smaller problem. But if the last word does not equal each other, then we need to add 1 to the minimum of these three numbers. So these three numbers are actually corresponding to the substitution error, deletion error, or the insertion error that are committed by the speech recognition system. So you find the minimum number of these three and add that by 1, and you get the new result, and which is the result for the bigger problem, given the smaller problem's result. So here is the initialization step. In the initialization, you can either specify added distance between an empty reference and a hypothesis with length m. So in this case, all of the words in the hypothesis are hallucinated. All of them. So the number of insertion errors are m. And in the other case, you can compute n of n and 0. So there is a reference of n words, but none of them are present in the hypothesis. But actually, the hypothesis is an empty sequence. So the edit distance in this case is n. So all of the references are deleted. There are n deletion errors. So we can write up the first column and the first row into this table. And the entries in this table are n of n and n. So each row corresponds to a word in the reference, and each column corresponds to a word in the hypothesis. So for convenience, we also include a start of sequence and the end of sequence token. So the initialization step allows us to fill in the first row and the first column. For example, let's see with the empty reference, if we write the hypothesis how to rec, then there are 3 words in the hypothesis, and all of these 3 words are hallucinated. So the edit distance is 3. All these 3 are insertion errors. And then we can go to the induction step. So we can go from row by row and from column by column. And one very interesting thing is that at the time of computing every single cell, we already know the 3 cells that are used to decide. So if there is an insertion error, then we take the left, we go left and go up by 1 step. And if that is a insertion error, then we go right. If it is the deletion error, we go down. But here we can see that this word in the reference equals this word in the hypothesis, and both of them are Hall. So we just copy the item of the smaller problem, which is the result of the smaller problem actually equals the result of this bigger problem. In this case, it's 0. Then we can take a look at the other items. And here, Hall does not equal 2. So we need to take a look at the smallest number of these 3. And in this case, it's 0. So we need to add 1 to this number to get 1. And in this case, we add 1 to 0, and this gets recorded insertion error or hallucination error. And following a similar approach, we can fill in the remaining items in the table and result in the final answer. So the bottom right cell actually includes the answers to the overall problem. So that concludes the computation of the word error rate. Actually, it concludes the computation of the edit distance. You can divide that by the length of the reference and multiply by 100 to get the word error rate. So that concludes how to evaluate the performances of the speech recognition systems. By the end of this lecture, you should be able to describe the listen, attend, spell ASR model and describe how to evaluate the ASR system. And optionally, if you are interested in practicing some coding of dynamic programming algorithms, you can do question 72 of LeetCode. So in Friday, Amanjit is going to give a tutorial about how to use SpeechBrain for doing the automatic speech recognition. And if there are some questions about the assignment 3, feel free to post on Piazza, and we're going to answer that as soon as we figure out the result. And see you on Friday.